So after listening to that riveting tale of gravitation, let's get into the concepts of gravitation. The first thing that we'll discuss are Kepler's laws. The first law of Kepler basically says that not only do planets revolve around the Sun, but they do so in elliptical orbits. And therefore, the first law is also known as the law of orbits. So basically, the first law says that every planet revolves around the Sun in an elliptical orbit with the Sun at one of its foci. And around the Sun is the orbit of not only the Earth, but all the planets of the solar system. Actually, Kepler's laws applies for all bodies that are orbiting a massive structure, and therefore you can see the universal nature of the application of Kepler's laws. Kepler's second law basically says that the line joining the planet with the Sun sweeps out equal areas in equal intervals of time. To understand this, let's take a look at a diagram where we have a planet and the Sun, and this planet is revolving around the Sun in an elliptical orbit. And Kepler's second law is saying that this line, which is basically the line joining the Sun's center and that of the planet, this line is going to sweep out equal areas in equal time intervals. Which means that if I start looking at this planet at a particular instant of time, and let's say that I observe this planet maybe for a day, maybe for 5 hours, but for some fixed interval of time, then as this planet moves in the orbit around the Sun, I will see that it will sweep out a certain area. This white line, that is the line joining the center of the Sun and the Earth, it's going to sweep out a certain area as it moves for a given period of time. And then I say that at some later time, I will again observe the same planet. And I will observe it for exactly that same amount of time. So let's say I had looked at it for 5 hours before. Now also I will look at it for 5 hours. And now I will see that it has reached some other point, and if I look at it for 5 hours, I will see that the same line is now sweeping out a different kind of area. And now I will compare the area of these two blue-shaped structures. Now these two blue-colored triangles may look very different to us, but Kepler says that the area contained within these two blue triangle-like structures is exactly the same. So of course, this structure looks very long and pointed, and this structure looks short and fat, but the area within these two blue-colored structures is exactly the same. And that's why Kepler's law is basically telling us that the aerial velocity, which is the amount of area covered per unit time, which I will say as dA by dt, is exactly the same for all intervals of time. And therefore, I will say that dA by dt is nothing but half r cross v. And now from here, I will convert this formula from a formula of velocity to a formula of momentum, and I will replace v with p by m, and therefore I get the formula as half r cross p by m. But we know that r cross p, where p is the linear momentum and r is the distance from the center of the Sun to the planet, this is nothing but the angular momentum of the planet, and therefore I have said that dA by dt is constant, which means that L by 2m is constant, and in general, because the mass we consider to be constant, we are basically saying that the angular momentum is constant, and therefore Kepler's second law is essentially a statement on the conservation of angular momentum. Kepler's third law is also known as the law of periods. Now, the planets are basically revolving around the Sun in a periodic motion. Let's take, for example, this Sun and the planet Earth revolving around it. But we also have other planets revolving around the Sun, and all of them are in periodic motion, which means that once they complete a revolution, they go right back and start performing another revolution. For example, the time period of revolution of the Earth is 365 days or 1 year, because that's how much time it takes for the Earth to complete a revolution around the Sun and start doing it all over again. Now, this time period of revolution is something we also call as the orbital period. This is the time taken by a planet to complete a revolution around the Sun. And Kepler's third law is basically saying that the square of this orbital time period is directly proportional to the radius of the semi-major axis of the orbit of the planet. Now that's quite a mouthful, Simplistically speaking, if I just write it mathematically, I am saying that t square is directly proportional to a cube, or I can say t square is directly proportional to r cube, where a or r is nothing but the radius of the semi-major axis. So let me show you what I mean. For the Earth, it is this line that forms the semi-major axis, whereas for Jupiter, it is this line that forms the semi-major axis, and the length of these lines is what is a or r. And basically, therefore, Kepler is saying that depending on the planet, it will have some orbital time period, that is t, and this t square will be directly proportional to r cube or a cube. Now, the importance of Kepler's law lies in understanding that not only does this law relate the time period of a planet to its own orbit, that is, the shape of the orbit will decide the time period, but it also relates one orbit to another orbit. And why is that? Because it is saying that t square is directly proportional to r cube, which means that t square upon r cube is a constant. It is a number, and once you have found this number for any one planet, you can use this constant number to find out the information about the time period or the radius of a different planet, because this number would be constant for all the planets. So like I already told you, after Kepler gave out his 3 laws, everyone wanted to understand why exactly this was true. Now the 3 laws perfectly fit the empirical data, and that's why they're also known as empirical laws. Empirical laws are those which were formulated only depending on observations or experiments made, and that's exactly what Kepler did. He just saw something and tried to make a model that fit his observations, but we still didn't know why this happens. We didn't know why the planets were revolving in elliptical orbits, we didn't know why time periods were proportional to cubes of radii, and we definitely did not know why exactly the aerial velocity was constant. And then came along Newton and gave his universal law of gravitation, which solved this wonderful mystery. So the universal law of gravitation basically says that every particle in the universe attracts every other particle with a force of gravitation whose magnitude is directly proportional to the product of masses and inversely proportional to the square of distance between them. Now, before I begin to explain to you what the statement for universal law of gravitation means, I want you to take a step back and understand why this was such a big deal. The universal law of gravitation was groundbreaking because it essentially connected the physics of the skies to the physics of stuff happening here on Earth. It was connecting physical phenomenon like why apples fall down from trees to why planets revolve around the sun. Before this, people thought that the physics of stuff that happens on Earth was different from the physics that ruled the night sky. But when Newton came along, he said, no, look, the same rules that apply to the skies also apply here on Earth. And that was amazing. And that's exactly why we call it the universal law of gravitation. We don't call it the Earth's law of gravitation. We call it the universal law of gravitation because it essentially governs the working of all cosmic structures, essentially anything that has mass. And you can see how amazing this statement itself is, because the statement is not talking about objects on Earth. It actually says that every particle of matter in the universe, it applies to every particle of matter in the universe, and that's why the universal law of gravitation is groundbreaking. So therefore, you need to understand firstly that this law is valid for all types of objects that have mass. For example, if I try to find out the force of gravity of the Earth on the moon, then I can apply the universal law of gravitation. But the law says that this is applicable to every particle of matter in the universe, which means I don't only need to have Earth and moon. I could have a plane and a car, I could have a pencil and a rubber, I could have a cheetah and a girl, and all these objects would be valid. You can find out the law of gravitation, that is the value of gravitational force between any two objects that have mass. And that's the first thing you must remember, that the law is defined for two objects, that is, you are defining the gravitational force between two objects. So let's get back to the Earth and the moon. Now, the first thing that the law says is that the force between these two objects, essentially the force between any two objects that have mass, is directly proportional to the product of their masses, which means that if I replace one of these objects with a heavier object, then the force between them should increase because the product of their masses has increased. And therefore, I say that every particle of matter in the universe attracts every other particle of matter in the universe with a force which is directly proportional to the product of their masses. Direct proportionality means that if the product increases, the force increases. But this force is also inversely proportional to the square of the distance between them, which basically means that the distance between these two objects, essentially the distance between their centers, if this distance is increased, then the force will decrease, and it won't just decrease, it will go down by the square of the distance between these two objects. And therefore, we say that the gravitational force is inversely proportional to the square of the distance between the two objects. And now, if I have to write down the formula for gravitational force, remember that force in itself is a vector, and therefore I must also talk about the direction of this force. And now you must understand that when you are talking of gravitational force between any two objects, you are actually talking about the force of one object on the other, but that is exactly equal and opposite to the gravitational force exerted by the other object on the first. Let me first write down this formula and explain this to you once again. The formula that we will write down is F bar 1, 2, where I will say it is the gravitational force exerted on mass m1 by m2, and it is denoted by writing 1, 2 in the subscript. So I say it is the force exerted on m1 by m2. This is equal to minus g m1 m2 by r square, r cap with a subscript of 2, 1. Let's take a look at what these different elements mean. So first of all, we have the product m1, m2. We also have the square of their distance in the denominator, that's r square, which is essentially the distance between the centers. And this is the way we write down the formula for the gravitational force vectorially. And remember, this is the formula we have written down for the gravitational force exerted on mass m1 by mass m2. Now, two more things I want to tell you. One, what is the meaning of the minus sign? The minus sign essentially means that the force is an attractive force. In contrast, if you ever write down a force which is a repulsive force, it would be written down with a plus sign. Finally, I also want to talk about this symbol G. G is nothing but the universal constant. It was definitely not there in the statement of Newton's law of gravitation. We just said that it's proportional. But because of this proportionality and its nature, this value was later on found out with very extensive measurements done by Cavendish, and its value was later put into this equation, and we called it the universal constant capital G. So this is the vectorial behavior or nature of this formula. Now let's move on to the question that if that was the force exerted on m1 by m2, then what is the force on m2 by m1? And the answer is that the strength of the force is exactly the same, but the direction is exactly opposite. So now you can see by yourself that the force exerted by both of them is actually the same, only their directions are exactly opposite, which means that whenever you are considering the gravitational force between any two objects that have mass, they each exert the same force on each other. But if you think about it, that also means that the gravitational force exerted by the earth on you is equal and opposite to the force that you are exerting on the earth. And that is an interesting statement. Now let's look at our formula of universal law of gravitation. Here I have written it down in its scalar form. I'm only talking about the magnitude of the force, and it is given by g m1 m2 by r square. F is the gravitational force between the two objects of mass m1 and m2. G is the gravitational constant. m1 is object of mass m1, m2 is the object of mass m2, and r is the distance between them. Essentially, if they are spherical objects, the distance between their centers. So now I've already told you that the universal law of gravitation is applicable to any objects that have mass, which means that I can use the same law to decide what is the motion of objects on Earth. So I should use this same law to understand why an apple falling from a tree is falling straight down. So that means I am trying to find the gravitational force exerted by the earth on all objects on the earth, which means that one of these two will always be the mass of the earth. So I replace m1 by the mass of the earth, and therefore m1 becomes capital M, which is the mass of the earth. Now m2 will be the mass of any object on which you want to decide what the gravitational force of the earth is. So I replace m2 with small m. Now I'm ready to look at the formula. This is the gravitational force exerted by the earth on any object of mass m. When Newton gave his universal law of gravitation, it was able to explain Kepler's laws, because not only did he give us this law alone, but he also gave us Newton's 3 laws of motion and also invented calculus. So we can actually take use of Newton's second law of motion to understand the motion of objects on the earth. If you look at this formula, I can take the mass of the object of mass small m to the other side, and this will basically become acceleration, because from Newton's second law we know that acceleration is nothing but force divided by mass, because we know F is equal to ma. So I take this m to the other side and I now have a formula for acceleration, and this is the acceleration with which objects fall on earth. Why is this specific to earth? Because this capital M was nothing but the mass of the earth, and therefore A is the acceleration due to the earth's gravity that objects will feel if they fall towards the earth. Finally, remember that this is a very specific case. You can also find out the value of this acceleration on a different planet, but for the earth we have a special letter to denote the acceleration, and we actually call it the acceleration due to gravity. So this A is nothing but small g. So small g is the acceleration due to gravity, and it is given by capital G, capital M upon r square. And it is this small g which has a value of 9.8 meter per second square, the acceleration with which all objects fall to the surface of the earth, including an apple falling from a tree. So we found the formula for acceleration due to gravity, which is nothing but the acceleration of all objects which are falling towards the center of the earth under the effect of gravitational force alone. And we found this formula to be small g equal to capital G m upon r square, where capital G was the universal gravitational constant, capital M is the mass of the earth, and r is the distance between the object and the center of the earth. Now, most objects are not that far away from the earth, so we can consider the total distance between the object and the center of the earth to simply be the radius of the earth itself. And once we consider that, we can also write down the formula for acceleration due to gravity in terms of the density of the earth, and finally I will get g is equal to 4 upon 3 pi rho gr. And this is the other formula for acceleration due to gravity. And this is actually a very famous formula. You might not recognize it because right now I haven't told you what this number stands for, but you should know by now that g is the acceleration due to gravity, which is 9.8 meter per second square. But what does it actually mean? We've heard of this number many times. This number is actually saying that all objects that are falling towards the earth are all falling with the same exact acceleration if it is only the gravitational force of the earth acting on them. But 9.8 meter per second square might not be that magical a number after all. We actually see a variation or a difference in the value of acceleration due to gravity because it depends on a variety of factors, the first of which being height. So let's take a look at the variation of g with altitude. The variation of g with respect to altitude is given by the formula gh, where this is the new acceleration due to gravity at a height h from the surface of the earth, equal to g into bracket r upon r plus h the whole square, where h is the height of the object from the surface of the earth. So if you're trying to find the acceleration due to gravity at a certain height from the surface of the earth, then that height is this small h given in this formula. So as you can see, the acceleration due to gravity is not a constant number, but varies as you move higher and higher from the surface of the earth. But sometimes, even when you go to a large enough altitude, you might think that the height is a large number, But as compared to the size of the Earth, h could be quite small, and therefore in those cases where the height of the object from the surface of the Earth is very small as compared to the radius of the Earth, in those cases the variation of g is given by a different formula, which is gh is equal to g into 1 minus 2h by r the whole square. And this is only when the height of the object from the surface of the Earth is very small as compared to the size of the Earth. Now from this I can write down the variation of g with altitude and represent it in a graph. If I plot a graph of acceleration due to gravity with the altitude or height, I will see that it varies inversely with the square of the distance, and therefore I get this curve as you can see in the graph, and this represents the variation of g with height. Now the other factor on which acceleration due to gravity depends upon is the depth from the surface of the Earth. Now if you think about it, acceleration due to gravity is just a consequence of the gravitational force, and gravitational force depends upon the mass of the object which is exerting this force. So let's say I go from a point on the surface of the Earth to a point inside the surface of the Earth, that is up to a depth d from the surface of the Earth. Now if you think about it, the amount of Earth that can exert a gravitational force on this point will be reduced greatly, because now the outer layer of the Earth can no longer attract this particle. It is only the amount of Earth which is below the surface of the object which can attract the object towards the center of the Earth. Remember, gravitational force is a force attracting an object towards the center of the Earth, and therefore when the object is at a depth d, it is only the Earth below the object which can exert a gravitational force on the object. Now because of this, the mass of the Earth which will be taken into consideration is greatly reduced. You no longer have to take the capital M, which is the mass of the Earth, but you will take the reduced mass of the Earth, that is basically the mass which lies within this new sphere that we have denoted. And once we do that, we can find out the acceleration due to gravity at this point at the depth h, and it comes out to be g into 1 minus d by r. So this is the formula for the variation of gravitational acceleration with depth, where d is the depth of the object from the surface of the Earth. Now from this formula we can plot the acceleration due to gravity versus the depth of the object from the surface of the Earth, and it's very obvious to see that it will come out to be a straight line. This is because d lies in the numerator and it has a linear relationship, and you will get a linear relationship which gives you a straight line starting from the center of the Earth, which is denoted at the origin, up to r, which is the surface of the Earth. The variation of g depends upon one other factor, that is the rotation of the Earth. To understand this, we first have to define what is known as the latitude. If we observe the motion of a point on the surface of the Earth, then we will see that as the Earth rotates about its axis of rotation, this point describes a circle, which means that every point on the surface of the Earth is actually undergoing uniform circular motion. Thus, centrifugal force comes into play. The line joining the point of observation with the center of the Earth makes an angle with the equatorial plane. This angle is known as the latitude. Capital R is the radius of the Earth, and small r is the radius of the circle that each point describes as the Earth rotates. The variation of g with latitude is then given as follows. The acceleration due to gravity, g, for a particular latitude is equal to g minus r omega square cos square lambda, where omega is the angular velocity of rotation. It is clear then that acceleration due to gravity increases with lambda and decreases with omega. The value of lambda is 0 for the equator and 90 for the poles. Thus, g has the highest value at the poles. And this is the cause for the difference in the value of g between the equator and the poles. Just like other forces, gravitational force also has the ability to do work, which means every time you see an object having some mass, it has taken some work to bring all those different pieces together and hold it together. And this work is stored in any object of mass in a certain form which we call as the gravitational potential energy. First, let's understand how this happens. So we have a specific formula in which we say that these objects or this mass comes together to form that clump that you can see. We will say that this whole clump is formed piece by piece, and when we say piece by piece, we actually say it is formed with 1 unit mass at a time. So first thing we will define is the gravitational potential, and gravitational potential is the amount of work done in bringing a unit mass from infinity to a point without acceleration. So we say that when an object of mass m is being created, it is being created unit mass by unit mass, and each of these unit masses are being brought from infinity to a point, and therefore the work done in bringing only 1 unit mass from infinity to a point is what we call as the gravitational potential. And the formula for gravitational potential is capital V is equal to capital G upon R into capital M. The minus sign tells you that the force for which you are writing the gravitational potential is attractive. Here small r indicates the distance of the object at its final position from the center of the earth, and therefore if I am bringing a unit mass from infinity up to the surface of the earth, then the final distance between that object and the center of the earth is nothing but the radius of the earth, and therefore we say that the gravitational potential of a unit mass at the surface of the earth will be minus capital G capital M upon capital R, where capital M is the mass of the earth and capital R is the radius of the earth. Most importantly, you must now understand that gravitational potential is defined for a single point. You always ask the question, what is the gravitational potential at a particular point? And then you find out what is the distance between that point and the center of the earth, and that's your R, and then you understand that it has taken V amount of work to bring this unit mass from infinity up to that point. Now, after we understand the concept of gravitational potential, the next obvious concept is the concept of gravitational potential energy. Similar to gravitational potential energy is also defined for a particular point. So now I'm asking, what is the gravitational potential energy of a body at a particular point? And if you see the definition, the gravitational potential energy, which is denoted by capital U, is the amount of work done in bringing a body from infinity to that point against the gravitational force. So what is the difference between the formula for the potential energy and the gravitational potential? Well, first of all, you are saying that you are defining gravitational potential energy for the whole body. Gravitational potential was the amount of work done in bringing a unit mass from infinity to a particular point, whereas gravitational potential energy is the amount of work done in bringing the whole body from infinity to a particular point, again against the force of gravitation. So here the formula for gravitational potential energy U is equal to capital G, capital M multiplied by the mass of the object small m divided by r, where r again is the distance of the object or the point at which you want to find the potential energy from the center of the earth. So here U is equal to G M upon R is the formula for gravitational potential energy at a particular point. Finally, we also ask the question, what is known as the gravitational field of the object or the intensity of an object which has a certain mass? Gravitational field is nothing but the area or the space surrounding a body in which you can measure its gravitational force of attraction. For example, if I want to find out the gravitational field or intensity due to an object of mass m at a particular point, which is a distance r from the center of this object, then the formula for the gravitational field or intensity says that E due to the gravity of this object will be capital G, capital M upon R square, where capital M would be the mass of this object, small r is the distance between the point at which you want to find the field and the center of the object whose field you want to find, and r cap is merely the unit vector in the radial direction, that is the vector pointing from the center of the object of mass m radially outward, and of course of unit magnitude. Douglas Adams once famously said in his book, The Hitchhiker's Guide to the Galaxy, that flying is just learning how to throw yourself at the ground and miss. Now, what exactly did he mean by this? Well, we see objects flying all around us. We know we've sent trips to the moon, we've sent missions and satellites far away from the surface of the Earth. How are all these objects managing to overcome the gravitational force of the Earth, and exactly what velocity do I need to throw these objects at so that I can achieve this feat? So if you remember, you must have learned projectile motion in laws of motion and in motion in 2-dimension. When we learned projectile motion, we saw that every time you throw something at the ground, it obviously falls down after taking a parabolic path. But have you understood what this actually means? Let's try to recreate the scenario of projectile motion, but at the size of the Earth. Now, as you can see, I have a cannon placed here which is going to shoot some cannonballs. Obviously, this is not to scale, but I'm trying to make a point. I'm going to shoot a cannonball from this cannon and I'm going to watch what happens. As the cannon pours out, I can see that it falls back to the Earth at some distance. And this is exactly what we call projectile motion. We also learned that the path of this object would be parabolic. But have you ever thought what would happen if I throw this with a high enough horizontal velocity? Let me try shooting another cannonball with a higher horizontal velocity. Watch what happens. The cannonball now moves further ahead but falls back to the Earth. And now I will say that if I keep doing this, increasing the horizontal velocity with which I throw my projectile, at some point the projectile is going to miss the Earth and be able to orbit the Earth. And therefore, it is this velocity with which this object will miss the Earth completely and take the circular path back, which we call as the orbital velocity. But of course, then the next logical question is, what happens if I throw it with even larger velocity than this? If I throw it with a velocity greater than this, what happens is that the object is now able to overcome the gravitational force and simply flies away from the gravitational pull of the Earth up to infinity, provided of course nothing else attracts it to itself. And this is what we mean by escape velocity. And that's exactly what Douglas Adams was talking about. Flying or moving away from the Earth is nothing but throwing yourself at the ground but missing. And that's what is happening to the object with the velocity in the yellow orbit and to the object with the velocity in the green orbit. What is exactly happening is that they are also being thrown towards the ground, but with so much velocity that they miss the ground completely. And therefore now we can define the velocities, orbital velocity and escape velocity. For the white orbit here, the velocity would be very less, much less than what we will call the orbital or the critical velocity, and so will it be for the blue orbit here. But the yellow orbit has what we call as the orbital velocity or the critical velocity. It is a velocity which lets this projectile complete an orbit around the Earth. And this green orbit is what we will call as the escape velocity, the horizontal velocity which the object needs so that it can overcome the gravitational pull of the Earth. Let's now define what they are one by one. Orbital velocity or critical velocity by definition is the minimum horizontal velocity of projection at which the satellite is any object that revolves around the Earth, at which the satellite revolves around Earth in stable circular orbits. So these are orbits in which the satellite will not fall back down to the Earth. So the velocity with which you'll have to throw it, the horizontal velocity, is what we call as the orbital or critical velocity of a satellite. It is given by the formula Vc is equal to r root g upon r plus h, where g is acceleration due to gravity, r is the radius of the Earth, and h is the height at which you want to launch this satellite, at which you want to launch it into an orbit. Now this is a general formula for the orbital velocity of a satellite. At any point you can launch it at any distance, but it is obvious then that the velocity that is required to launch an object into orbit depends upon what height you want to launch it at. If you want to launch it at a lower height, you'll need a higher velocity. If you want to launch it at a higher height, you'll need a lower velocity given its inverse relationship. The formula if you want to launch a satellite very close to the surface of the earth is given by Vc is equal to root capital Gm upon r, which can also be written as root gr, since we know that g, that is acceleration due to gravity, is capital G capital M upon r square. We can also rewrite this formula for the satellite revolving very close to the earth in terms of the density of the earth, and it will be given as Vc is equal to 2r root pi rho g upon 3, where rho is the density of the earth, and we get to this formula simply by replacing the mass of the earth with the product of density into volume, and volume we know is 4 upon 3 pi r cube because we assume the earth to be a sphere. Finally, we can also define the time period of a satellite. The time period of a satellite is nothing but the time it takes to complete an orbit around the earth, and it is given by t is equal to 2 pi root r plus h cube upon gr square, which is equal to 2 pi r divided by the critical velocity vc. So this is the time period of the satellite. We can also understand what is known as the escape velocity by looking at its definition. The minimum velocity of projection so that you can overcome the gravitational pull is what is known as the escape velocity, and therefore objects that want to fly off into space need to have velocities which are at least the value of the escape velocity, and of course if you want to go even further ahead with some velocity, you need to have velocities greater than the escape velocity. The formula for escape velocity is VE is equal to root 2gr, very famous formula. A lot of problems are asked on the concept of escape velocity. Root 2gr can also be written in terms of the density of the earth. It is r root 8 by 3 pi g into rho, where rho is the density of the earth. So escape velocity VE is the velocity with which an object should be thrown horizontally so that it just overcomes the force of the earth. However, if you throw an object with a velocity greater than the escape velocity, then it means that the body will have some velocity when it goes into outer space, because not only has it overcome the gravitational force, but now it has extra energy to even move around in space, and therefore it will have some velocity in space which will be called as v dash, and given by the formula v dash is equal to root v square minus ve square, where v is the velocity with which you have thrown the object and ve is the escape velocity or the minimum velocity required to overcome the gravitational pull. So we saw that when an object is launched with a horizontal velocity which is equal to the critical or the orbital velocity from the surface of the earth, it goes into what is known as a stable orbit around the earth. So it's basically going to orbit the earth, and this is what we call a satellite. A satellite can be defined for any object as long as it's orbiting that object. So for example, we know that the moon is a natural satellite of the earth. However, we also have many artificial satellites which we use for different purposes like watching TV or getting internet access or even for military purposes. So we need to find out what is the energy of this satellite. The first thing to understand is when the satellite is moving or orbiting around the earth, the only force acting on the satellite is the gravitational force of the earth. However, we have launched it with some velocity, and therefore it's going to have some kinetic energy due to that velocity, but it will also have potential energy only due to the gravitational force of the earth. So if I try to tell you what is the energy of the orbiting satellite, the first type of energy that it possesses is the potential energy. And since it's only moving under the effect of gravity, this potential energy is the gravitational potential energy. And gravitational potential energy is nothing but the multiplication of the mass of the satellite by the gravitational potential. So I can say it is m into v, where v is the gravitational potential. And we already know, because we've learned this previously, that the gravitational potential is nothing but minus g capital M upon r, and this multiplied by the mass of the satellite, which I say is small m, will give me that the potential energy is minus g m upon r, where capital M is the mass of the earth, small m is the mass of the satellite, and r is the distance of the satellite from the center of the earth. This can also be written in terms of angular momentum, and we get the formula minus L square upon mr square. Angular momentum L is nothing but linear momentum multiplied by the distance, so that is nothing but mvr, and if you put that, you will see that these formulas are the same. So this is the gravitational potential energy possessed by a satellite. But like I said, it also has kinetic energy. And it has this kinetic energy because of the speed or the velocity with which we launched it from the Earth. And we know the formula for kinetic energy is half mv square. So the kinetic energy of the orbiting satellite is half mv square, and we know that we had launched it with an orbital velocity. So we know that v here is nothing but root gm by r. If you put that into the formula for half mv square, you will see that the kinetic energy comes out to be g capital M small m upon 2r. Now keep in mind that the kinetic energy is positive. In fact, kinetic energy can never be negative. However, the gravitational potential energy was negative. The negative sign for the gravitational potential energy was telling us that this object is attracted towards the Earth. Kinetic energy, however, is positive, giving us g capital M small m upon 2r. This again I can write in terms of angular momentum, which will be L square upon 2mr square. Finally, now that I know what is the potential energy and the kinetic energy, I can write down what is known as the total energy of the orbiting satellite. So if I simply add the terms of potential energy and kinetic energy, I get the total energy of the satellite, that is minus g capital M small m upon 2r. See that the total energy of the satellite comes out to be negative. This negative sign tells us that the satellite is attracted towards the Earth, that there is an attractive force acting on this object. In fact, this is one of the ways we understand whether an object will orbit the Earth or no. If the total energy comes out to be negative, it means that it is bounded to the gravitational influence of the Earth. As long as this total energy is negative, you can be sure that this object will not escape the gravitational influence of the Earth. So this negative sign is not a small deal. Again, I have written this also in terms of the angular momentum, and the total energy comes out to be minus L square upon 2mr square. But we also define what is known as the binding energy of a satellite. Now, binding energy is defined for a satellite in this way. Binding energy is the minimum amount of energy that we have to supply this satellite so that it can escape the gravitational influence of the Earth. And this is very simple to understand. We already know that the total energy of this satellite was minus gmm upon 2r. Now, how much energy would you have to supply so that it goes away from the Earth forever, that is to free it from the energy of the Earth? You simply have to supply a binding energy equal to minus of the total energy that it already possesses. So you can see that the binding energy required is g m m upon 2r. And here r is capital R, that is the radius of the Earth. If the satellite is very close to the Earth, we are neglecting its height from the surface of the Earth. However, if the satellite is at a height h where the height h is not negligible, the binding energy comes out to be gmm upon 2 r plus h. R plus h is nothing but the small r that we have been writing so far. Although there are many different types of artificial satellites, there are two very specific types of satellites that we will study today. One of them is the geostationary satellite. A geostationary satellite orbits the Earth in a geostationary orbit. Geostationary orbits are those in which a satellite, when orbiting the Earth, appears stationary relative to the Earth. And this is because its orbital period is 24 hours, which is exactly equal to the rotation of the Earth. So a geostationary satellite will orbit the Earth in 24 hours. Not only that, its sense of rotation is the same as that of the Earth, that is from west to east. And finally, geostationary orbits are those which are at 36,000 kilometers from the surface of the Earth. Geostationary satellites usually orbit above the equator. So this is what we call as a geostationary satellite. They are used for communication purposes, for TV broadcasting, for global positioning systems, that is for our navigations that we use in our phones, and even for defense and intelligence purposes. Another type of satellite which is very useful to us is the polar satellite. Polar satellites are those which circle the globe in north-south orbits passing over the north and south poles. Now, the time duration or the orbital period of a polar satellite is 100 minutes, which means it passes around the Earth many times a day. However, because the Earth is rotating below the polar satellite is actually able to image different points on the Earth. And because of this, polar satellites are used for imaging the different points of the Earth, and they can produce complete images of the Earth's surface. And that's why one of the most important uses of the polar satellite is imaging for weather conditions. The clouds are actually moving below them, and therefore they can image for us the weather conditions like dust storms or winds and volcanoes, etc. Finally, we come to the definition of weightlessness. Weightlessness is nothing but a condition. It is said that a body is in a state of weightlessness if its observed weight is zero. And by now you should know that observed weight means that we just feel like the weight is zero. It's not that the weight is actually going anywhere. An object is said to be in a state of weightlessness when it is freely falling. That is because it is falling down with the same acceleration with which the Earth is pulling towards it. And therefore, effectively, it doesn't feel like anything is pulling it at all. And therefore, an object which is freely falling is said to be in a state of weightlessness. So this wraps up all the concepts that I want to revise with you in the chapter Gravitation. I hope you understood the different concepts and were able to quickly revise with me the important points and fundamentals that you will require for problem solving.